This video explains making an LED nightlight that is activated by an ultrasonic sensor with battery backup based upon a Joule thief circuit. Full details of the build are given as I step through the design and construction. See the notes in the description if you want to skip directly to a particular point in the build. If you find this useful, I appreciate if you can take the time to like, comment and or subscribe. Stumbling around in the dark one night, getting out of bed led to the idea of some sort of automatic nightlight. This resulted in a design for a nightlight that is automatically triggered by breaking an ultrasonic beam, which turns off after a set time, powered by a single A4 battery, which makes the project compact and inexpensive. Before getting into the details of construction, here are the items that you will need for the project. The LED light is based on the Joule thief design, like this version for a different project using the dead bug style to avoid needing a printed circuit board, but I use Veroboard in this project. So you need an NPN resistor, ferrite toroid for winding the coil and a couple of resistors, all items that can be easily bought or salvaged from disused electronics. I'll show you how to salvage the needed parts like the toroid from a broken CFL light globe. A high power 1 watt LED or similar, a HCSR04 ultrasonic sensor module, a couple of dollars from eBay, an AT-Tiny 85 DigiSpark module, again a couple of dollars from eBay. The micro USB version has advantages as enables power from a phone charger. A light dependent resistor as a light sensor, so the ultrasonic sensor will only trip on during the night time, a couple of buttons, and a suitable enclosure or housing to mount the components. I designed a custom housing that has a rotating mount for the sensor and LED, but this can be anything suitable for your exact purpose depending on your imagination and materials. A quick list of features of the project and then we'll get into the design and construction. The nightlight uses a high brightness white LED that is triggered by tripping the ultrasonic beam. A single toggle button being pressed down sets the LED on time in steps of 1 minute up to 5 minutes. The number of flashes equals the selected time. The ultrasonic sensor sensitivity is similarly set in steps of 25 cm up to greater than 1.5 meters by the toggle button. The 3D printed enclosure allows changing rotation and elevation of the sensor and LED. The light sensor only enables LED power on during night time, that is the preset darkness level. 5 volt power is provided via a standard phone charger, and in event of mains power outage, the white LED is automatically powered on via the Joule thief circuit using a single AA battery. I started with the notion of using the Joule thief circuit, which is a type of voltage booster, to power the white LED, as this has minimal, easily available cheap parts, and moreover allows the use of a single AA 1.5 volt battery, enabling the final design to be compact. I wanted the nightlight to be normally off and to be triggered when waking from bed in some manner for a set time, so the Joule thief circuit needed to be augmented with a timer and some sort of sensor. While there are many potential options such as the ubiquitous 555 timer chip, the DigiSpark module only costs about $2 from eBay and provides onboard timers, analog to digital converter, PWM output etc. with 6K of program memory and a 2 square centimeter PCB ready for mounting. So the DigiSpark module would provide the timer functionality and conveniently could then also digitally control the Joule thief circuit for powering the LED via a simple NPN transistor switch. While the DigiSpark module could directly power the white LED with a suitable transistor to switch the needed higher current, I continued to use the Joule thief circuit as this enabled the white LED to be battery powered, and in case of mains power outage, the Joule thief battery powered part of the circuit would automatically take over, so give a nice backup nightlight even in the event of a power outage. With the DigiSpark module, using the HCSR04 ultrasonic module is relatively trivial, and this gives a nice solution to automatically turning on the LED when getting out of bed, by just having to put your feet down when standing up. One downside of using the DigiSpark module is that it requires 5 volt input, However, there are DigiSpark modules with mini USB connectors that accept standard phone chargers, so 5V DC power is not a problem and doesn't require extra components. Since there are still a couple of I/O pins left in the DigiSpark module, I use one for the toggle switch to enable user input to set the on-time duration of the LED. Also needed to enable setting the sensitivity of the ultrasonic sensor. While could have used another toggle button, instead used the final I/O pin to read a light-dependent resistor. The LDR thus has two functions. Firstly, if the light level is lower than a set level, it is then assumed to be nighttime, and only then will tripping the ultrasonic sensor turn on the LED. And secondly, the state of the LDR determines which setting the toggle switch affects. The LDR in the light means the toggle switch changes the LED on time, while the LDR in the dark means the toggle switch changes the ultrasonic sensor sensitivity. A nice side benefit of incorporating the Joule Thief circuit is that some of the necessary parts can be had for free from a broken CFL light globe, in particular the ferrite toroid. If you don't have a CFL light globe handy, ferrite toroids can also be had for free from any other salvage sources, such as broken power supply cabling, etc. But the CFL light globe provides a small toroid that gives a compact outcome that I was aiming for in this particular project. Taking all the usual safety precautions, you can be as gentle or not in taking apart the CFL globe, but obviously dispose of the glass parts carefully. Since all types of fluorescent bulbs contain mercury vapour, there is some risk if you break the actual glass part. Although only a small amount of mercury is involved, no mercury exposure is safe, so deal with this appropriately. Once you have the internal circuit board removed, time to move on to desoldering the actual components. Desolder and remove the components of interest from the disassembled CFL globe. The capacitors can be useful, the transformer, the NPN transistors can be used in this actual project, but the main item of interest is the ferrite toroid. Now comes winding the coil on the toroid for the Joule Thief. You need two pieces of enamelled wire. I reuse wire salvaged from the CFL globe and use pieces of different colour to help ensure that I alternated the wires as they were being wound. Obviously you need enamelled or otherwise insulated wire. The chopstick helps keep things nice and neat, which is relatively important to ensure that the coil later works in the circuit. The number of loops is not critical. Use as many as fit neatly and evenly. I ended up with an inductance of about 200 microhenries when finished. Make sure you alternate looping the wires, keeping the winding in the same direction, and don't overlap the loops. You will need some sort of enclosure to house the various components. This can be whatever you have that is suitable, but I have a 3D printer, so designed a custom enclosure in Fusion 360 that enables movement of the sensor, has internal channels for cabling, and consists of all 3D printed parts that clip or screw together without the need for other hardware. Depending upon your exact requirements, the enclosure solution probably requires allowing movement of the sensor housing, as the ultrasonic beam is relatively directional. The HCSR04 spec is an 8-degree beam angle, and this also gives more flexibility when physically mounting the completed unit. Some time lapse of the actual 3D printing of the enclosure. Skip ahead if you want, but there is something about watching a 3D printer doing its thing that is fascinating and a little mesmerising at times. Before starting the final construction of the project, I first did some test runs to check that the various major components actually fit in the enclosure, and that their planned location and orientation would allow access to physically handle and install the necessary items. The enclosure has various parts that enable 3D printing without needing supports, and ease physical access to install components. This was an iterative process and resulted in this end design. Internal channels are provided in the enclosure parts to enable routing cables from the sensors to the control electronics. This makes for a tidy solution that eliminates the possibility of a user snagging or breaking wires. A design having everything in the one box, so to speak, would have been easier, but the rotating mount type style ultimately makes for a less intrusive look when actually mounted beneath the bed and orientated for correct operation. I made a wiring diagram and VeroBoard layout schematic to help keep things correct while doing the installation. Using different coloured wires also helps with this. With the wiring installed, you can now move on to soldering and installing the various electronic components. Firstly, solder the HC-SR04 ultrasonic sensor using the appropriate leads. Recommend using some heat shrink to ensure no accidental shorts between pins later when installed in the enclosure. Then the white LED. Obviously check that the cathode and anode are the correct way around. And finally, the first stage is finished by adding the light dependent resistor. With the sensors connected to their leads, fit the HC-SR04, LED and LDR into the enclosure. Tidy the cables and then close up the sensor housing. With the sensor housing completed, you can now attach and route the cables into the circuit housing, and then you are ready to solder up the components onto the VeroBoard, which make up the Joule Thief part of the circuit. I used VeroBoard to mount the components for the Joule Thief portion of the circuit, and made a wiring diagram in the VeroBoard layout schematic to help get things correct when soldering the various items. Mounting and soldering the various components is relatively straightforward. Double check the NPN transistor orientation before soldering this item. Also, the layout I used includes a couple of tracks in the VeroBoard that need to be cut. These are denoted by the red zigzag lines on the schematic. Best to do this before soldering the components. The Joule Thief coils also have a specific orientation, so double check this before committing to soldering the coil to the VeroBoard. With the Joule Thief components on the VeroBoard, you can now do the first test. Hook up the LED and a AA battery and the LED should illuminate. If the LED doesn't illuminate, possible things to try first include checking that the LED cathode and anode are connected the correct way around, that the enamelled wire from the coils was stripped properly where it is soldered to the VeroBoard so that you have a good conductive joint, the orientation of the NPN transistor, and any solder bridges etc. on the VeroBoard. When the Joule Thief powers the LED correctly, then you just need to connect the various leads to the AT-Tiny85 DigiSpark module and the project should be ready for final testing. Well, that's about it for the actual construction. What remains is some discussion about the firmware that utilises the input from the ultrasonic sensor to control the LED, and how the user can change settings such as LED on time and ultrasonic sensor range via the single toggle button. Another benefit of using the AT-Tiny DigiSpark module is that the firmware is relatively easily written and uploaded using the Arduino IDE. I don't think people would want me to step through the code line by line, but if so, leave a comment and I'll see about a separate video if enough interest. The code is available on my website, so I'll only give a high level overview here. Central to the firmware is the NewPing Arduino library. This enables easy initialization and reading the ultrasonic sensor. The main loop consists of first checking the various inputs, that is the state of the LDR and the toggle switch, and then reacting appropriately depending if the LED is currently on or off. If the LED is currently on, that is, the sensor was previously tripped, a timer is checked to determine if the LED should remain illuminated or not. If the LED is not illuminated, the ultrasonic sensor is checked, and if a signal within the set range is detected, the LED on status is changed, as long as the LDR is below the set limit, i.e. it is in the dark. Finally, if the toggle button has been pressed, after some software debouncing, either the LED on time, if the LDR is in the dark, or the ultrasonic sensor range, if the LDR is in the light, is set according to how long the user holds down the toggle switch, and then the main loop repeats. Okay guys, hope this was of interest. If so, I would appreciate if you could take the time to like, comment and subscribe.